This is a very essential derivation of the equations of motion with constant acceleration, what we typically refer to as our kinematic equations. And I'm going to do it without using any calculus at all. That is, I'm going to do it in an algebraic way. I can get away with this sort of a cheat by doing things in approximation. I'll explain that approximation as I go along. Where I'm going to start here is with the very simple and obvious notion that the final position is equal to the initial position plus the average velocity multiplied by time. So this is my starting point. It's where I'm going to jump off. And what I'm going to do is make algebraic replacements here and do a little bit of algebraic manipulation till I get to a place where I want to be. Now this equation is absolutely true, and it says something obvious. If you want to know where you're going to be in the future, that is x, then you start with where you are now, that is the initial position, plus the average rate at which your position changes multiplied by time. So what's of interest to me is how I'm going to define this average velocity. As I'm defining it here, the average velocity, which that bar over the velocity stands for the average, is going to be the initial velocity plus the final velocity divided by 2. And that's not surprising, because that's how I calculate any average. I take a certain number of things and I add them up and divide by the number of things. Here I have two things, the initial velocity and the final velocity, and so I add them and divide by 2, giving me the average velocity. Well, naturally the thing that I'm going to do here is I'm going to take that average velocity and substitute it in. Being able to do substitutions like this and get decent results out of them is a big part of being successful at doing physics, but it also, according to me, is a big part of the fun. So I have the initial velocity plus the final velocity divided by 2 that I stick in there, and then I have this t here on the end. So now I've taken an equation that was rather compact and I've made it look a little bit more sophisticated. I shouldn't let that be daunting. It's going to be okay. I'm heading in a particular direction. You may say, well, I wouldn't have known to do those things that you did. Well, the reason why I'm doing them is because I'm heading for an equation that has a certain practical value to solving physics problems. So in this case, it is sort of because I know what I'm doing. Notice here that I have the initial velocity in the numerator and I also have the final velocity. Well, I have another equation for the final velocity. That is that the final velocity is equal to the initial velocity plus the acceleration multiplied by time. If you don't see immediately where this equation comes from, it comes from the definition of acceleration. Acceleration is the change in velocity divided by time. So a little algebraic manipulation of that, and I have this equation. What I'm going to do is I'm going to take this v right here, and I'm going to plug it in where it appears there in the top of the equation. I'm going to make a direct substitution. And so I find myself writing this again, that x is equal to x naught plus, and now a pretty big quantity here, the initial velocity, which is still there, plus the initial velocity plus the acceleration multiplied by time, and all of that is divided by 2. And I can't forget that I have a t on the outside here to go along with this t on the inside. I didn't draw terribly well. So now, in a very real sense, I'm done with my derivation. I just need to write it in a more compact and more familiar form. So what I'm going to do here is with the numerator, I'm going to group those terms together. Again, because I know where I'm going, I know what I expect it to look like in the future. What I'm going to do is realize here that I have v naught plus v naught, and so that's 2 v naughts that I have written there. And I'm also going to multiply that by t, because there's a t on the outside here that's going to multiply through. And I'm going to add to that the acceleration multiplied by t, but now also multiplied by t. So there's a t squared there, and I'll close those brackets and recall that this whole thing is in fact divided by 2. Now, I'm not quite done because I want to get rid of the parenthesis by dividing both of these terms by 2. And when I do that, I'll get an equation that is very familiar and satisfying. The final position is equal to the initial position plus the initial velocity multiplied by time plus 1/2 of the acceleration multiplied by t squared. And that is one of our fundamental, I suppose I'll try to put a box around it, that is one of our fundamental kinematic equations that we use every day to solve problems of motion with constant acceleration. The assumption of motion with constant acceleration, by the way, was applied up here. This expression for the average velocity is only true when I make the assumption that the acceleration is constant. That is, that the velocity increases by equal amounts and in equal intervals of time. So that's pretty good as derivations go, but this derivation has a second half to it. Because x is equal to x naught plus v0 t plus 1/2 at squared is only one of the kinematic equations that I use on a regular basis. So what I'm going to do is start this derivation again. And when I start it again, as it happens, I'm going to start from the same place that I started before. The final position is equal to the initial position plus the average velocity multiplied by time. Now, just because I'm starting from the same place doesn't mean I'm going to end in the same place, because I'm going to choose to go sort of in a different direction this time. I'm going to use the definition of acceleration. That is, that the acceleration is equal to the final velocity minus the initial velocity divided by time. And you might argue that this is what I did in the last version of the derivation, but what I'm going to do this time is I'm going to solve this around for time. That is, time is equal to the final velocity minus the initial velocity divided by the acceleration. So since that's the time, what I'm going to do is go back to my initial equation here and substitute it in for time at that location. So I have the final position, x, is equal to the initial position plus, now I'm going to leave the average velocity alone, but I'm going to take a step in the right direction by appreciating that that average velocity is the initial velocity plus the final velocity divided by 2. I used that in the last derivation. And now I'm going to multiply that by my value for t, which is the final value minus the initial value divided by a. And once again, with just two simple substitutions, I find myself, I'm at the end. I've actually achieved my goal. But again, I don't have it in the algebraic form that I would like. So what I'm going to do is a little bit of algebraic jiggery-pokery to this. The first thing I'll do is realize is that I have two fractions being multiplied here, and I have a 2 in the denominator and an a in the denominator, and I'll factor those out. It'll clean my equation up quite a bit and help me make a little realization here. The final position is equal to the initial position plus 1 over twice the acceleration multiplied by the initial velocity plus the final velocity multiplied by the final velocity minus the initial velocity. Now that makes me immediately want to FOIL these two quantities together. So what I'm going to do is take this, I have x naught here, I'm going to subtract it to the other side. When I subtract x naught to the other side, I'll have x minus x naught over there, and that is delta x, the displacement. So subtract the x naught over, and then I'll multiply the 2a over the other side of the equation. So I have 2a multiplied by delta x is equal to this funny business. V initial plus V final multiplied by V final minus V initial. And so what I'll do here is I'll FOIL these. And when I do, I'll find that the cross terms cancel, and I'm left with the final velocity squared minus the initial velocity squared. This equation is not yet in its final form, not the form that I used it in. What I'm going to do is add the initial velocity squared to the other side of the equation and flip it so I get the equation in its very traditional looking official form. That is, that the final velocity squared is equal to the initial velocity squared plus twice the acceleration multiplied by the displacement delta x. And that is another of my very familiar kinematic equations derived with algebraic means.